in Korea, it's very late right now, so thanks for staying up for this talk. It's relatively early here in California. Um, so, so today I'm going to tell you about some of the tools that we've been working on in our group that are intended to help people develop codes. And that's a kind of basic philosophy of the software that we generate in the group. So we want to create software that's not only useful for performing calculations, but software that's useful to help people write code, develop new methods, and use them for purposes that we sort of never thought of, even when working in our own research. So I'm going to give a little bit of the talk, but two of my co-workers, Huan Chen and Johnny, are also going to be speaking. All right, so the packages I'm going to talk about, there's going to be three of them. PyCF, this may be in this community the package that people have heard of, and this is the general molecular materials electronic structure platform. So I will be talking about this, but I'll also tell you about two other libraries, or my co-workers will. So one is PyBlock. This is a new DMRG and matrix product state code intended for easy development from Huan Chen. And then finally, Johnny will tell you about his really fabulous QUIM package. And this is really more of a quantum computing development tool, but as the intersection between quantum computing and quantum chemistry grows, then perhaps this audience will also be interested in QUIM. Okay, but first let's talk about PyCF. Okay, so PyCF, the name we decided after coining the acronym, we decided the name should be Python Simulations of Chemistry Framework because it sort of just fits into the acronym PyCF. And by now this is a large-scale effort and many contributors to the code. We recently wrote a paper and that described some of the ideas behind PyCF. But even though it's a community code with many contributors, by far the most important person and the person who really started the project and was the main architect, continues to be heavily involved today, is Qiming Sun, who's also going to be speaking later in this conference. So many of the ideas for how PyCF is structured and much of the implementation is from Qiming. So it's a general purpose platform for molecular and materials simulation. Oh, I also highlighted here one other person, Xing. We will notice if you're a participant or on the message board of PyCF today that Xing is the main maintainer of the code in my group right now. So you also see him a lot. Okay, so it's a general purpose electronic structure platform for molecules and materials. And in putting the library together, we had sort of three unique principles, at least we think they're unique. So there are many, of course, advanced and fantastic quantum chemistry software packages and platforms out there. So, why did we create a different one? And it was really because we wanted to set up a platform with the following principles. One is we wanted to be able to create a library that empowered users to implement their own methods, not necessarily just use the ones that we provide. We wanted to support molecules and material simulations on an equal footing. So it's not just quantum chemistry, but also material science. And finally, we wanted this to be a library which extends beyond chemistry, in which people could use as a component of machine learning and quantum computing. And by some metrics, we feel that this project has been successful in these regards. For example, if you just look at GitHub as one metric, the number of projects that use PyCF as a dependency, so this is a core part of their own code, is well over 100 by now, approaching 200. Okay, so the code inside PyCF is written in a certain style, and if you look at it, it's largely Python-based code. But the style is really set in the following follows the following rules. Okay, so first is that because we want this really to be a developer's library, it's made of lots of small functions, and those small functions are for each of the tiny tasks that you'd imagine in a quantum chemistry code. Whether it's building integrals for each shell to doing certain bits of the Hartree-Fock calculation at DIS. They're all just tiny functions, and those functions are pure functions for the most part, which means you can call them without state anywhere. You can call them in any order. And to make it very easy to pern with, the API is such that most of the arguments, input and output, are very straightforward arguments, basic data types, no complex classes. And so this is an example where you set up a molecule, you run Hartree-Fock, and the coefficients are just returned to you as a simple NumPy array. And let's say you want to do integral transformations, then you just pass in an array to this object and returns the integrals as another NumPy array. Okay, so it's just easy to work to deal with the inputs and outputs. Now the implementations are also intended to be easy to work with on the inside, right? So if you read a specific algorithm like CCSD, we don't want it to look too complicated. So one way in which we handle this is that often we provide two implementations, one which with the same API, one which should be very easy to modify, like this is like code from the easy CCSD code. And then, certain parts we also provide with the same API an optimized version of the code. To achieve competitive performance, we rely, heavily on specific libraries being heavily optimized. So PySF is 90% Python, so Python is not a high-performance language per se, but you can of course work in C-based libraries, and so we have heavily optimized libraries for the integrals. This heavily optimized for vectorized instructions like AVX2. All the tensor contractions go to specialized libraries, which again are heavily optimized, and so on and so forth. And then because most of the code is written in Python, then you can benefit from the dynamic typing of Python and change things easily at runtime. So, many things are implemented, so it's a fairly full-featured package today. And it's fairly performant in that you can also treat large problems with it. There is a parallel drop-in module, MPI for PySF, where many of the core functions have MPI versions with the same API. So you can just drop in this module and then the code will run in parallel. Now, as I mentioned, one of the key things we wanted to achieve was a unified infrastructure for molecules and materials. And how did we go about doing this? So ordinarily, this is kind of hard because the language used for crystal simulation and molecule simulation is kind of different. People use different approximations, different data sets, and so on and so forth. But if you set things up in the right way, material simulations can actually be made to look almost the same as molecular simulation. And then the code you write can be basically the same for both. Okay, so roughly speaking, we set up our material simulations so that, for example, we use crystalline Gaussian bases, which are of course then very similar to molecular Gaussian bases. We implement k-point symmetry in such a way that it just looks like the implementation of point group symmetry, but with a larger group. In crystals, you have complex orbitals, of course, but if you write your molecular code so that it can deal with complex orbitals, then it's the same code. And perhaps the most important thing is how you deal with the Coulomb interaction in crystals. And the basic point is that in crystals, often, for example, you might want to use FFT to do things because of the periodicity, but that's just the same thing as density fitting with plane waves. So if you structure your algorithms so that they all use density fitting 3-center intermediates or 3-index intermediates, then the crystalline code and materials code will look the same, even if the underlying Coulomb infrastructure for evaluating the potential can be swapped out, for example, using FFTs rather than Gaussian integrals. So in this way, by sort of setting up the formulation of the problem the right way, then you can write, if you write a function for molecules that takes complex orbitals and uses density fitting, then the same function can usually be used in PySF without any modification to treat crystalline materials. And so as an example of this kind of write once but run for both molecules and materials philosophy, this is just what code would look like if you wanted to run calculations in molecules on the left and materials on the right. So the molecular case, you set up the cell, you set up the integrals, and then you have all these methods that are being run, and both these scripts will run whether you're doing a molecule material. But the important point is that these commands here and the implementations behind them are exactly the same under the hood. Okay, so there's only one piece of code that is doing both. And for users, it's the same. You could write one piece of code on the left and one piece of the code on the right. Subject to certain conditions, it will run for both. As a more advanced example of developing with PySF, here I show just what you need to write to create a method that we don't have in the package as a native method. This being orbital optimize MP2. Okay, so we have MP2, right, but we don't have orbital optimize MP2. But what do you need to do? Well, this is a complete code to do orbital optimize MP2 and run a calculation. And all that we do here is that we write a little bit of wrapper code around MP2 itself that makes MP2 look like full CI. And the reason why we want to do that is because if you're doing full CI, we have orbital optimization for that in the code. That's called CASSEF. So CASSEF takes full CI and does rotate the orbitals. And so we simply make MP2 of the same API as a full CI object, then it will work inside CASSEF. You know, the functions don't have other state. And so that's what we do. So MP2 is just wrapped so that it has the same arguments as a full CI object, and it returns a density matrix. And then we just pass it to CASSEF, which calls the full CI functions without any underlying state. And then this will perform orbital optimization. So that's really a simple example of how you can generalize the code. Okay, so it's an active community project. I mean, this is all I'm going to say about PySF because we've got other things to talk about, and many people contribute to it all around the world. I actually don't know if we have Korean contributors. We might do. I would just say, you know, for some purposes, I think it's a great package.